Okay, let's give you guys some more practice. So here I've got a 10 by 10 flat cardboard sheet. Okay, so this is 10 by 10 here. And then we're going to cut this square out, cut this square out, cut this square out, and cut this square out. So we're going to create an open top box. So this bit will fold up, this bit here will fold up, this bit here will fold up, this bit here will fold up to create our open top box here. Okay, so the question is, well, if this here is 10 by 10, what must x be to create the biggest volume? Okay, so we're going to create an open top box, meaning that we've got a base at the bottom, but at the top there's nothing here. Okay, so it's going to be a box. Find x here where the volume will be the greatest. Okay, so press pause and have a go. Okay, so to do this here, if this is 10, if this is 10 by 10 here, okay, then this this length here must be 10 minus 2x, because if you think about it, this here is x and this here is x, so this length here must be 10 minus 2x, and the same goes for the vertical one here. So this is x, so this length here must also be 10 minus 2x. So this area here will be 10 minus 2x squared. Okay, and then you've got to times the height. The height here will be x. So anyway, think about it. The volume here will be given by this. Okay, which can also be written as this. Okay, squared. Okay, well anyway, the volume is given by this. Blah blah blah. That will then multiply it out. It will then give you this. Now, once you're here, just quickly sketch a graph in your mind or on paper, just to get an idea of what's going on. So here we're going to try and sketch this graph here. So at the moment it's v equals blah 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 here. Okay, so let's sketch a graph of let's sketch this graph. So this is v, this is x here. So when x is big, it wants to do a positive cubic. So we know it's going to do something like this. Hang on. It wants to do a positive cubic. Okay, and when x is small, it wants to do a straight line here going through the origin. So it goes through the origin because there's no intercept here. Okay, so it goes through the origin, gradient of 100, so it's pretty steep, and maybe give it a bit of a negative quadratic here. Okay, a negative quadratic because of this. Okay, just a tiny bit, and then so when it's big, it wants to do a positive cubic. When it's small, it wants to do a line with a gradient of 100. So we're going to guess it to be something like this. Okay, and then when it's big, it wants to do a positive cubic. So we're going to guess it to be something like this, and then it's got to curve down. We're going to guess it to be something like this. Okay, and so this graph here will look something. This graph here will look something like this. Okay, maybe let me extend it so it looks prettier. So maybe something like this. Maybe it touches like that, or maybe it goes over like this, or maybe it just touches slightly. We don't know. Okay, so let's just say like this for the time being. So now our domain, if you look at our domain is actually in where our domain will be greater than 0 and less than 5, because if you look at our cardboard sheet, well, if x is 0, then you're not going to have a box. You're just going to have a flat sheet of cardboard. If x is if x gets to 5, then this here will be 5, and then this here will also be 5. So you're not really going to have a box here. So let's just limit our domain to greater than 0, because if it's dead on 0, then it doesn't really make sense. So our domain will be in between here. So hang on, let's draw a graph again. So maybe something like this. Okay. So our domain will be 0 and 5. Okay. So we want to find. So remember, this is a volume here, x here. We want to find the maximum volume here. So find out when the gradient of this line here will be 0. So find the gradient when it's 0. So here we've got a graph v versus x here. So let's just blindly differentiate v with respect to x, whatever that means. Okay. So hang on. So currently v equals this. Hang on. Sorry. Hang on. Let me go back one step. So our domain here is between 0 and 5 here. So our graph will look probably something like this. I don't know. So this here is 5 here. Let's just double check where. Well, hang on. It could be something. It could be something like this. Okay. So our domain here is between 0 and 5 here. Let's just check where the value when x equals 5. When x equals 5, let's check where this point here will be. So let's so the volume is given by this, and then v bracket 5 here will be given by this, and then so when x equals 5, the volume will actually be 0. So now we know that our graph will look like this. Okay, so we know it's going to be 0 here. Don't forget, our graph could actually do something like this. Touches here and then go up. It might not even cross into the negative realm. But let's just let's just say it crosses over. So it's going to be between 0 and 5 here. So we want to find out when the gradient will be 0. So here we blindly shut off our brain and just differentiate v with respect to x, whatever that means. Okay. All we care about is we want to know where the gradient will be 0. So v is given by this. Differentiate v with respect to x. So that will then give us this here. Okay. And then blah blah blah. Set this to be 0 because we want to know when the gradient will be 0. So try and solve this. So now complete the square. So from here divide everything by 12. That will then give you this. And then well, just do whichever method you want. There are lots of ways of doing this. Basically, you're currently here. dy by dx equals this. Find out when the gradient will be 0. So it's really you solving this. Okay. Use whichever method you want. So here, divide everything by 12, and then blah blah, and then so it's really you completing the square here. And if you don't know what completing the square is, watch one of the earlier sections. Okay. So here, yeah, your eyes, when you get to this stage here, your eyes will zoom into this. You're always going to need half of this. Well, blah blah blah. That would then take you to well, when you're here, simplify it. It will then give you this. Blah blah blah. X equals this. Okay. So so x equals this. So what that means is, hang on, what does this mean? It means x equals this, or it equals this. Okay. This simplifies to this. This simplifies to this. Now we've limited our domain to be less than 5. So let's forget about this. It's meaningless when it's dead on 5 because, well, let's forget about this. So this is the one that we're interested in. Okay. So looking at this here, our graph now looks like this. Okay. This here is when the gradient, when x equals this here, the gradient will be 0 here. So this here is our critical point here. Now we need to find out the critical value here. So which is this point here. So v equals this. Work out when x equals 5 over 3. So that's this bit here. 5 over 3. Put that in, basically put 5 over 3 into the v, and then that will then give you this, and then blah blah blah. It will then give you this. So what that means is that when x equals 5 over 3, our critical value here will be this. This here is our biggest volume here, and this here 5 over 3 is what we should cut the what we should make x to be. Okay, so hang on, 5 over 3. So what that means is looking at our original question. Hang on. Looking at our original question, wait there. Hang on. Yeah, looking at our original question here, this we should cut for the maximum volume. We should cut this to be 5 over 3. So make x to be 5 over 3. And when you make x to be 5 over 3, it will give us a volume of 2000 over 27. Okay?